And then like if although I want to travel like there, it's dangerous, right? So that's why I need to go for that.
Yeah. Also uncomfortable.
Yeah, to reduce my risk.
Yeah. Wait till you're old.
Yeah. I have enough to die.
And it's also bigger things how much of the investment on one thing.
It's also uncomfortable. Like
People start
exactly.
Like 10 years with one moment.
Okay, let's get started. Welcome back, everybody. Announcement, review sessions. So yesterday I couldn't make it just because of the conditions outside. So I didn't want to drive around. My internet was down, it's up here. So normal stuff. Ankur, I'm curious, what was your probability that you would be in class this morning?
After yesterday, it was like a 1.
Oh, okay. So it's like, that's the whole question. It's like, what about on Wednesday?
On Wednesday, it was like probably half and half.
Yeah, I think we should try to keep track of these things in our head. And like, mine was pretty high, but it's just because of the last 2 flops on storms. You never know what you're going to get around here. Yeah. We'll always improvise. So, we'll come back to this example in just a moment, but I canceled the review session yesterday, and the best I could think of what to do, since next Thursday is spring break, and I think if we did do a review session anyway, you guys would feel guilty if you missed it, so we're not going to mess with that. So, I think what we'll do for reviews is the next 2 Mondays I have time. We also have office hours after class. So if I can't accommodate you at this time, let me know. We'll figure something out. So that review sessions, are going to be 5:30 p.m. for the next 2 Mondays. So this coming Monday, just to be specific about what I mean by the next 2, this coming Monday I'll do a review session at 5:30, and the following Monday I'll do a review session at 5:30 as well. Just to give you some time to get through your homework is what I was kind of thinking. I was really opposed to the idea of giving a review session this Monday and Friday. So the homework was supposed to be due in a week's time. We'll just push that back a little bit. So you could turn it in on Wednesday if you'd like, if you need some more review session. But what I do recommend is get through your homework, because I'm going to give you new homeworks next Friday as well. So new problems to work on. So you should be working a couple problems every day. So if you want to get good at this stuff, you work on it every day. So not just all at once. So that's my best advice. But homework postponed until I think it's the 3rd of March. That's pretty late for this homework to turn in. It's about a week late. So stay on track, and if you need any help with the problems, because there's some hard ones in there, stuff worth discussing also, come to the review sessions or see me after class. So thanks for the patience on all of that. We're going to come back to this, and then we're going to mention some preliminaries to the delta method. And I'll point out, before we even start that, this is what I would call an asymptotic frequentist result. What's the frequentist stuff in there? I guess the stuff that you might do with the intervals that you might build using the delta method. The method will be good if n is fairly big. So I'm always thinking this, the method gets better and better as n goes to infinity. I hope we're all asymptotic frequentists in some sense. That as n gets bigger and bigger and bigger, we do better and better and better. So in some sense, as n goes to infinity, if n were infinity, all of our methods, if they were consistent, would give us the exact answer. And so usually, this isn't good enough for me to say things like this. As n goes to infinity, things get better and better. And what we might describe as coverage rates actually are achievable coverage rates. What I really want to know in my techniques is, does it work for the size of data that I actually have? And so all of the theory that we're going to discuss in the delta method doesn't answer that question. And so we never know. And so the answer is always a simulation study. So I'll have you play around with this in practicality. We'll do a few math problems with it. But I want you to study like how this method actually can work and how it can fail. And so we always want to think about that with techniques. I think the book's a little optimistic sometimes, where it says, here's the technique, and under these conditions, everything works. I always want to know, when does it fail? So tell me that part too. Hopefully you guys get into the mindset of doing that for people in the future. We're a little optimistic in our results. I also said that this is a classical technique. So that means it's old. And when I see people invoke it, it better be for theoretical reasons and not practical reasons. You know, I think it's a little old-fashioned. Sometimes I see it still used, and I chuckle. So anyway, you'll have your own opinions about it. It can work, and it's worth discussing. Okay, so back to this problem that we were studying. We want to figure out what the density function is for the range and the mid-range. So the mid-range is just the max and the min. Added together, divided by 2. And the range is the difference between the two. If we want to find this distribution, we're going to use 2 steps. So step 1 is write down the joint distribution of the min and the max. We know how to do that. Step 2, transform. And so this equation right here, at the end of the day, what we wrote down was this simplifies to n times n minus 1. That's going to be these terms. Over here, when I plug in that j is the max and I is the min. So times write this down. This is going to be times 1 over alpha squared. So that's these two things. Each one of these is 1 over alpha. And these things right here are going to be x n over alpha. This one right here is going to be x1 over alpha. That's the cumulatives that we figured out. So this is going to look like 1 over alpha squared times x n minus x1 over alpha. And this is going to be raised to the n minus 2 power when I plug everything in. And that's what we have. We should probably write down what the conditions are on all of this so that we fully describe this distribution. So this thing isn't fully described until we end up saying what the valid ranges for xn and x1 are. And so there is a constraint in here. xn is less than alpha, x1 is less than or greater than 0, and they bound each other. So all stuff that we already know. So let's just plug everything in to our transformation. So what we do when we transform this thing is we look at the inverse transformation, we plug everything in. Every time I see an xn, I plug in terms of the mid-range and the range, what that means. Same thing for x1. So F, R, M, and I'll say my dummy arguments are little r to m. This is going to be equal to F, xn, x1, whatever this function was right here, so it's this thing. But I'm going to substitute in r and m. So I'm going to rewrite in terms of xn and x1, r and m right here. 1 second. Times the Jacobian. Yes, please.
Can you write FRM? Shouldn't you write m plus r over 2, m minus r over 2?
Yeah, so what I'm going to actually do, if you just want it, this notation isn't exactly, so I'm going to write down this is xn, this is x1, and then I'm going to substitute in what my function, what this is. This is going to be m plus r over 2. And this one's going to be m minus r over 2. So that's what we're doing.
I mean the FR, the first on the left-hand side.
This?
Yeah, no, the lower script, a big R, big M, on that F.
Uh-huh.
Yeah, here. Is it right to write it Rn, not m plus? Because I think I've seen it rewritten the other way.
The random variables are going to be Rn. So I'm just denoting, in terms of notation, what this f represents. It's going to be the joint density for the range and the mid-range. So I think it's right. So again, it's just notation. So sometimes people use other notation, so it's good to get your head around that. So I think once we write this out, it'll just be clear. So I still have the n times n minus 1, the 1 over alpha squared. And then I have this function right here that looks like the range. So I substitute in the range for that. I'm going to write it in as little r and not big R, which would denote my space. This is just the dummy argument, raised to the n minus 2. And we're not quite done. So we have a Jacobian that we need to work out, and then we need to discuss the bounds on R and M. They have something to do with each other, and when we ended up simulating all of this quite a few weeks ago, we could see that there were some real constraints here.
It should be R over alpha.
Yes. Absolutely. Okay, so bounds on R and M, probably need to write those down. Good job. Let's just work through this Jacobian. The Jacobians, it's just a calculus exercise. I'm going to write down dx1, I'll say dm, dxn, dm, dxn, dr, dxn, oops, I already messed up, dx1, dxn over dr. I'll just point out, there's no correct way to write this in. You have choices. So what I usually do is I either fill out a row or a column. And I'll just write down the derivatives with respect to the same thing, and then I'll change the argument up top. As soon as I've specified that order, I have to keep doing it as that order. So keep in mind, Jacobians, if I flip things around, so if I interchange those, that Jacobian would just be the negative of whatever I did. And if I flip this whole row and I substituted it with this one, that would change it by a negative sign. So determinants are like that. We're going to be taking the absolute value of all of this at the end of the day. So absolute value on top of that. And so it doesn't matter which order you do it in. It's always going to be positive. So again, this is representing the chain rule in this transformation formula, if you want to think about it that way. I like the way Peter discussed it, and he said, when you're coming up with this one-to-one mapping in the spaces, and what you're doing is just showing how the volumes of that space transform. So a lot of times I think of this as the stretch factor on the space. So this is pretty easy right here. So dx1 dm, there's only an m sitting right there. So when I take the derivative with respect to m over here, that's 0. There's only one m here, so that's a 1. Similarly, this is a 1. And then when I take the derivative with respect to r, I'm doing x1, so that's got my minus sign right there. And so this is going to be a minus 1/2. This is going to be a plus 1/2. So pretty easy Jacobian to roll through. I like it when they're constants. So this thing is just going to be the absolute value, this times that, minus that times that. So this is going to be 1/2 minus 1 times a negative 1/2, if you will. So this is going to be a plus, plus. If you'd like to change that, so this is going to be 1 at the end of the day. So Jacobian's 1, that's always nice. Now we have to do the harder part of the problem. This is the part that everybody in all their calculus classes are like, how do I do this in high-dimensional spaces? And you can remember this exercise when you were in calculus, and hopefully you gave yourself some ways to think about the problem. But usually it's hard. So to visualize what everything is. So what I always do is I check the endpoints of everything. And then I think about the relationships between the variables after I do that. Usually do a couple double checks on all of this. But let's just think about what these bounds look like. So I'm going to draw a picture. I'm going to let this be R, and I'll let this be M. We'll change those to lowercase. So I'm going to let R just be free roaming, so I know where R can live. It lives between 0 and alpha. And so that's a little bit arbitrary. I could bring the bounds down and say M lives between 0 and alpha. And then figure out what the constraints are in terms of R. I'm going to do it the other way around. Well, I already know the range, xn minus x1. This thing lives between 0 and alpha. That's pretty easy to justify. This is alpha. I also know that the mid-range lives between 0 and alpha. And so, but it depends on R pretty heavily. I usually like to check just the endpoints of whatever I arbitrarily write down. So I'll think about what this looks like over here. So when the range is alpha, there's only one instance where the range can be alpha. So range is equal to alpha. I know that the xn has to be equal to alpha and x1 has to be equal to 0. And so, and I can mentally work that out for myself. And so that's corresponding to this point. Right here. So this is going to be this stuff. And I can figure out real quickly that when the range is alpha, this is the only thing that can make the range equal to alpha. So I want to maybe think about these points on the boundary of the space when R is equal to 0. So when R is equal to 0, I know that xn is equal to x1. And this can happen in a lot of different ways. So these can be equal to 0 maybe. So when they're equal to 0, that's this point right here. So then the mid-range is going to be 0. And xn could be equal to x1, and they can both be equal to alpha right here. And that's going to make the mid-range alpha. So again, I'm just thinking about the boundaries of the points. If I were doing a test, and I'll never ask you to do something like this on a test where you're thinking about the bounds. I remember my time as a tutor, where I was tutoring undergrad and graduate statistics. The only problems I would mess up on the fly are problems like this, where I'm working through the bounds of the problem, I'm scratching my head, and then I figure out, oops, I set down the wrong boundary conditions. So usually stuff you have to think about. I can look at these equations real quickly and see instantaneously that these are linear functions in terms of m and in terms of r. And so instantaneously, if I were rolling through this, I would note that these are linear functions. And so the things that connect these points that I've already worked out have to be straight lines. So that's kind of my cheap explanation of all of this. If you want a better explanation, just write down what m is. It's going to be xn plus x1 over 2. So that's the definition of this thing. There's no r's over here. So I would probably rewrite it in terms of r's and start substituting this thing in terms of r, and then later I would substitute that in terms of r. Let me just show you. So xn, just remember what the range is. Range is xn minus x1. So I can rewrite xn is equal to plus x1. So I might substitute that and say this is r plus x1 plus x1 divided by 2. So there's two x1s in there. This is going to be the range plus range over 2 plus x1. And I could rewrite this a little bit different. I could substitute in x1 into this, and that's going to be xn minus r. So I could write this down, or I could write this down. So this is going to be 2 times xn plus minus r over 2, which is going to be xn minus r over 2. And so I have 2 different ways that I can represent m in terms of r. And then I have to just think about what are the ranges on this and that. So what happens when this is 0? What happens when this thing is equal to alpha? So the biggest this thing can be, well, let's think about this one. The biggest this can be is alpha. And so what I might say is that since that's the biggest xn can be, m is going to be less than alpha minus r over 2. If that's going to be outside of my range, I might think about what this is when this thing is 0. That's actually going to induce that bound. Sorry, bound goes in the other direction when I plug in alpha. But if I plug in the smallest thing right here, then I know that m is going to be less than that. That is what I'm thinking of. So if I want to get the bound right. So again, you have to think about it for a second. I get messed up too on inequalities, and I have to think about what I'm writing down. So this is going to be bounded by that right here. What is that? That's this. And then I can maybe think about this equation as well. And I can think about how big and small this thing gets right here. And so m is going to be larger than whatever this thing is. So m is going to be larger than 0 plus r over 2. My 0 is right here because this is an element between 0 and alpha. So again, I just write it out differently and I think about what happens on the bounds of the function. If I were trying to be quick, I'd probably just recognize things are linear and start connecting lines and figure out what that line was. I would never ask you to do this on an exam that would be in class. If I ask you to do something take home, I might ask you to do it. So this class isn't about testing how much of your old calculus you remember or forget. But at the end of the day, we have this shape. And we saw that in our simulation. And so we finished this problem by writing down what the bounds are. So r goes between 0 and alpha, and m lives between alpha minus r over 2 and r over 2. And we're done. And so I have the distribution of the min and the max. And then maybe I can answer some questions about what the probability distribution of this thing is when I plug in different mins and maxes. And maybe if I were growing grapes somewhere, I would figure out maybe there's some regions where the probability of mins and maxes or the range and the mid-range are certain variables, certain values that are unacceptable for growing grapes. And so then I might say, probability of being in these extreme ranges is too high, so I'm not going to grow grapes there. Anyway, it's just a math exercise. The book extends this and they figure out what the margins on R are and M, and you can read through those examples. So just see what the marginalization is. Again, you're going to have to integrate either in this direction or in that direction to marginalize things out. I'll never ask you to do a very tricky integral on a time test. Any questions about this? Okay, so that's that. This problem is going to creep up over and over and over again in slightly modified forms through I think chapter 7 plays around with it a lot. So keep this example in mind. That's why we're going through it. I like this problem because it has lots of boundaries in it. And inferences with lots of sharp boundaries usually are a little bit more difficult when you don't have sharp boundaries. So just a problem for the future. Okay, let's begin delta method. Before we do delta method, I want to just recap something about Taylor's theorem, because that's what this is based on. So this is really just an asymptotic thing that uses a first order Taylor approximation. Taylor's. So what Taylor's does, just consider some function. A smooth function. How smooth? So that it has all its derivatives. So that's smooth. So g of something, I'll say g of x. So this is going to be my smooth function right here, and I can approximate it using the Taylor expansion. R goes from 0, I'll say I goes from 0 to R. I think that's what the book writes down, so we'll stick with the book's notation. G centered somewhere, I'll say centered at alpha, times x minus alpha raised to the I, and there's an I factorial down here. So these are the I derivatives. And we know something about the remainder. The remainder is just going to be, let me give this a name. I think they call this TRX in the book. So GX minus TRX is going to be equal to our remainder. And this thing gets really small. It goes to 0 as R goes to infinity. And so Taylor's tells us something about that. So long as you're within the radius of convergence. And this rate right here is bounded by the largest term in your approximation. So the remainder is bounded by the largest term. In TR. So i.e. that's going to be this term. GR, evaluated at my centering parameter, divided by R factorial, X minus alpha raised to the r. And so by studying this term right here, we can say something about whether or not this is going to converge and how fast it's going to converge. So that's what we have to look at. Okay. The delta method is going to utilize this. The delta method is actually a really cheap approximation. It doesn't use more than the first order term. So it ends up using a linear approximation, and I'll tell you why next time. So there is a second order delta method. I guess you could concoct a third order delta method, but it would be a disaster if you did it. So think about the reasons why that might be the case. What happens if you're reading over the weekend? Why doesn't anybody do the third order approximation in the delta method? We haven't set it up yet to really have a good conversation about it. We're probably about 15, 20 minutes away from it. So let me just tell you something else. That for multidimensional functions, we can come up with the Taylor approximation as well. So let's discuss some random variables. So let's just say that let T, cap T, be a collection of random variables. T1, T2, down to Tk. So these are random variables. They're the things that behave randomly. So if I go and get another instance, they flutter. And they flutter according to some distribution. The distribution we're going to be invoking for the delta method is going to be very specific. We're going to be studying random variables that are normally distributed. And so the full characterization of the delta method relies on normality, but let's just keep this general for a moment. And they're going to be random variables, and we're going to assume that they have some mean. I'll write it out like this. Theta cap. So this is my bold-face theta that I make. So if you guys don't know, so you might say, let's circle H. This is cap theta. And I use that notation a lot. So that's what I usually write on the board. And I'm going to say it's a collection of means. So I am presupposing that the means exist in all of this. And in the application of the delta method, if my random variables were normally distributed, I don't just have means, but I also have variances. And I have everything else as well. It's just that they're evaluated at 0. Those are the only interesting moments in the distribution. So I'm just going to write out that I can come up with an approximation. So Taylor approximation. For some function g evaluated at cap t, right here. So this is k-dimensional, right here. So I'll say this is k-dimensional. So this is going to be k-dimensional. So a lot of times, we're not interested in just the random variables themselves. We want to transform the random variables. So in delta method is a statement about transforming normal random variables. So it applies to things like x bar or something similar to it. A lot of things out there are normally distributed. So we're going to invoke some central limit theorem when we come in next time. So this is going to combine that CLT talk with this new sort of transformation thing that we're doing. So this is going to be say k goes from 1 to cap k. Let's just say 5 goes from So this is going to be approximately g theta This is the 0th order term in the Taylor approximation, and this is going to be my first order term. So this is going to be G prime. So this is just the first derivative. I'm going to plug in theta. I'll tell you how you deal with these derivatives in a second. So this is going to be the partial derivative. And I'll write down what that means in just a second. Times ti minus theta I raised to the first power divided by 1 factorial. So this is just a first order approximation. So if you didn't know that about Taylor's, this is how Taylor's works in high dimensional spaces, is you just take all these partial derivatives with respect to everything. These are, just to be clear about this, this is going to be the derivative of G cap T with respect to Ti. And then I'm going to evaluate all of the T's at thetas. So T1 is going to be evaluated at theta 1. T2 is going to be evaluated at theta 2 because that's my centering approximation. So on and so forth. Tk is going to be evaluated at theta k. So when I take a derivative of this function with respect to ti, there's still a whole bunch of t's laying around in it. I'm going to plug something in for them. And I've chosen to center my approximation at the mean. And it kind of makes sense. So you could center things at other values. But means are pretty good, especially when you're studying things like normal distributions, where the mean is kind of telling you where the mass of the distribution is. So it's a good estimator for the center of the distribution. Of course, in cases where you have like bimodality, you probably wouldn't center things at means. But it seems reasonable for now. So I'm just going to show you one thing with this. And I'm not going to go into too much detail here, and we'll pick up with this next time, just to motivate what the delta method is. So if we look at this, my expectation of GT, so maybe I'm trying to study whatever this random distribution is, some transform of some random variables. This is going to be approximately equal to the expectation of G theta plus all of this junk. And there's only one random thing in this. The only thing that's random in the equation in here is that. And we're in luck. This is linear. Expectations are linear, so this couldn't be easier to calculate. This is just going to be equal to the expectation of G theta plus some I goes from 1 to k, so I'm going to do a couple steps at once real quick. G I theta times the expectation of Ti minus theta I.
Is there a reason why we're using little theta and E of G theta?
Just because I was waiting for you to call me out.
And also, about the diagram. And
Which
also
one?
just
The one that you just corrected.
yeah.
Cool. Right on. It's good to have things right on the board. Please.
is the g function scalar?
Yeah, I mean, this is going to be some scalar function. It could be a lot of different things. So, but yeah, I'm thinking about it like that right now. But it could be a lot of stuff. It's a function. So it's going to map to some number. So we'll give more context to it when we start studying real examples, and maybe I should have done that. But this is going to simplify quite a lot. So remember what the expectation of the TIs are of their theta i's. And so all of this expectation is 0. This thing is just g theta plus 0. So at the end of the day, my expectation of gt looks something like g theta. So maybe that's a good approximator for whatever this thing is. And the question is how good of an approximator is it? So how closely close is this approximation? And as statisticians, we like answering that question. So how close are we? So we're always talking about something in terms of distances. A lot of times we're invoking probabilistic distances, but this is the question. How good of an approximator is it to that? And can we say anything else about this? And so we'll come back and we'll answer this question by looking at variances, and then we'll place some distributional assumptions on t. i.e. we're going to study what happens when it's normal. But what we're going to end up getting is if all the TIs are normally distributed, this function is going to be well approximated by a normal centered here, and it's going to have some variance that we can compute. So we'll look at the variance next time. In order to answer this question. But I want to just point out that we already knew stuff like this. So I already knew that maybe instead of looking at the expectation of gt, maybe I could look at g expectation of t. And I could swap these two things around. So that's just equal to theta, which is that. And so we knew stuff about this long before. So in your probability class, you learn about Jensen's inequality. And if you have some convexity conditions on G, you can even come up with bounds in one direction or the other. And so we kind of have always known that this thing is maybe close to that, but we don't know how close. And so what people have figured out a long time ago is that if we know what the distribution is and that t is asymptotically normal, that this thing will converge to some normal, and we can start answering questions about how close everything is. But there's the rub. And this is all going to depend on how close is this approximation to that thing in the first place. And so if your function is not close to being linear, this thing might not be very good at all. And also there's the question of how quickly do these become normals? And if they become normals very slowly, what we do with the delta method won't work either. So there's two things that are happening with the delta method that can cause it to not work well. i.e. the Taylor approximation is not very good, or the asymptotic rate of convergence to normality is slow. And so when I see people invoke this technique, I want them to answer both those questions kind of up front, why this is reasonable to even do. You might say if it's not reasonable, this approximation, you might start adding in other terms. So maybe I'll add in more terms. And those terms will look like things like functions of ti's minus theta i's squared. And then maybe I add in some other terms, ti's minus theta i's cubed. and I keep doing that, and I do better and better and better in my approximation, but there's going to be a problem. So I'll just kind of foreshadow this for you. Why we use the linear approximation. If the t's were normal, then this thing is normal, right here, this approximation. Why? Because everything is just linear, right here. So if the t's are normal, this has a normal distribution. Multiplying it by stuff and adding it together is still normal. And adding something else into it is still normal. If I added in these terms right here, now I've got normal plus chi-squared stuff. So this is normal. So when I square it, it's chi-squared. So I'm adding normals to chi-squareds. What distribution is that? No idea. If I start cubing out my normals, adding them to chi-squareds, adding them to normals, now I have some distribution. I don't even know what normals cubed are. So I really don't. I just call them normals cubed. No utility of that in my life. And so this method is easy to employ, but it only works under some conditions. So that's at least where we're going with it. So we'll pick up here next time, look at the variance, and then we'll make a statement of the delta method, and then we'll prove that it's true. And our proof is going to have to do with how fast this remainder is going to 0. So look through that, read through it, and the discussion should be fairly brief if we're all up to snuff with it. So we'll probably take another lecture to finish out the statement of the delta method. We might want to look at a couple examples. I can show you some examples where it works really good and where it doesn't work very good. And then we're going to move on to Bayesian methods. And so that is not in the book this soon. So what we're going to do is we're going to get a lot of tools, and then we're going to discuss those tools in context to each other. So I'm going to supplement a Bayesian lesson for you, and I'm going to add one to it. Hold on. Once we get into chapter 7, they go through Bayes there in the book. We will have already have done it, so we're saving time, I think. Okay. 1 minute early, so I've given you 1 minute back. That's it. Have a great weekend. And I'll give you the rest of the 20 minutes.